Newton-Raphson for implicit scheme. So I get many questions on these during office hours of how does it exactly work. So here I'm going to go a recap of how does Newton-Raphson work. So Newton-Raphson aims to solve. So it solves a general nonlinear set of equations. Okay, where let me write R and W also as a vector. Because in general, we are trying to solve a set of equations with a set of unknown variables. And the number of equations has to be exactly the same as the number of unknown variables. Otherwise, the problem is either overdetermined or underdetermined. Right? So the number of R is equal to the number of W. All right. So for example, when we do implicit schemes, this happens. For example, backward order a vector minus v of n is equal to of v n, right? Okay, what is the problem here? The problem is that when I want to compute vn plus 1, I need to say vn plus 1 is equal to vn plus delta t times f of vn plus 1. But I don't know vn plus 1 to start with. How can I compute vn plus 1? It's like a circular algorithm, right? So I can if it's a x, I can just so if it's an x-phase scheme, I can do this equal to vn plus delta t f vn plus 1. So for forward order, this is vn, and I can just plug in vn and compute vn plus 1. But if it's backward order, I don't know vn plus 1 to start with. How can I compute vn plus 1? So here is where I have to use Newton-Raphson. Here we realize that we can define R of W as W minus delta T times F of W. If we can define the nonlinear residual function like this, then if we can define R like this, and if we can use some method, for example, Newton-Raphson, to find the W that makes R of W equal to 0, then that W is our Vn plus 1. So make Rw equal to 0 is Vn plus 1. Right? You agree? Anybody have questions on this? So the problem of computing Vn plus 1 is simplified or abstracted to the problem of finding the 0 of this nonlinear function. So now let's forget about our scheme. Let's focus on finding just the 0 of that nonlinear function out here. Okay. Now, to find the 0 of this function, first, it's very hard, right? Because it's nonlinear and everything. It has sines and cosines, exponentials, garbage. So let's conceptually what if by approximating it as AW plus B, approximate it as a linear function? Anybody give me any suggestions of how do I find the 0 of that linear function? Okay. Find the eigenvalues of this matrix and then do what? So the question is, what is the W that makes R equal to 0, which in this case, if we can make the assumption, is what W can make AX plus B equal to 0. Okay, I get an answer that is negative B times A inverse. Anybody agree or disagree? Hmm? Can we split them? Yes. So this is I'm sorry. Okay. To find the answer, we multiply I mean very easy. This is very easy to compute, right? So every time it's better to just derive it. Just to multiply A inverse onto this equation. So to find W, we multiply A inverse onto that. It should be 0, right? You cannot multiply from the right because multiplying from the left is the only way of combining A inverse with A to make it I. Right? The recap on linear algebra. So if you multiply on the right, it doesn't work. You agree? Because you cannot exchange two multiplications in matrix algebra. So this IW is of course is equal to W. So W is equal to minus A inverse times B. Or in MATLAB, that is minus A backslash B, right? Again, I want to emphasize again, don't do inverse A times B in MATLAB. That is a very inefficient way of doing things. Doing A backslash B does not involve actually inverting the matrix. It actually just solves the matrix equation. It's much more efficient. Okay, so now to recap, if we can approximate the nonlinear function with a linear approximation, then the 0 of that linear approximation can be easily found by solving a matrix equation. Now let's get back to this. Now R is nonlinear. What would be a good linear approximation of R? Come on, you guys should already be an expert in Taylor series expansion, right? Doing all the truncation error stuff. So Taylor series would be a good way of approximating the nonlinear function, right? So W, let's say W0, we do Taylor. You guys should be an expert in that. Okay, R W is equal to R W naught. Anybody? Go on. Plus delta T. No delta T in R, right? Plus delta W, exactly. Delta W, which is really W minus W0, right? Multiplied with the derivative, which is partial R partial W at W0. Then plus higher order terms like delta W square. So yes, you guys are already an expert in Taylor series expansion, but only for one-dimensional functions. Now this is to get familiar with Newton-Raphson. This has to be a Taylor series expansion of multiple nonlinear functions. And here, partial R, partial W is a what? It's a matrix. Is a matrix now, where partial R is a matrix. Partial R1, partial W1, partial R1, partial W2, partial R1, partial W3, etc. And the second one is partial R2, partial W1, partial R2, partial W2, etc. and etc. Right? So the linear term would be a matrix. And please don't think what is the other terms left because it'll be more complex. So just to focus on the constant term and linear term. Okay, so we have a Taylor series expansion. These terms may be very ugly, okay, but the good thing is they are evaluated at W0, so they are not functions of W. So that helps in trying to find the zero of this Taylor series expansion. To find the zero, we can simply invert this matrix as W minus W0. Okay, is going to be equal to partial R, partial W inverse times R W0, and of course the minus sign. Right? That would be the zero of the first order Taylor series approximation. Right? And of course, that is not exactly what we want, right? That is approximately what we want because it is the zero of the first order Taylor series expansion of the function. So we can only see that W minus W0 is actually because we want the W to be the zero of the nonlinear function, and if we set it equal, then W is only an approximation of the linear right of the Taylor series expansion. So this is not exactly W, but hopefully better approximation of W than W0. That's why we set W1. W1 is the next better approximation than W0. And what is the purpose of that? The purpose of that is so that we can do again at W1, so that we can compute a W2 of the next Taylor series expansion. All right. Oh, everything should be super quick. Starting with the system. All right. Oh, this is 2. And it's actually one is equal to W times RWP. So at some point, the approximation should be so good that R of WP should be almost 0. And that's when we call it good enough and declare small, we declare victory and class is over. We declare that V at time step n plus 1 is actually just equal to this WP. Right? This goes all the way back to our numerical speed. Is solution of next time step. Okay, so conceptually we have gone through so much stuff, but we just